Okay, good afternoon everyone. Welcome to this workshop on eigenfaces. Um, so I know this is after lunch, so I hope all of you will stay awake, and of course that is my job to make you stay awake. So let's see. So how many? So just to get a feel for you know what type of audience I am talking to. Um, are you all? How many of you are like first year students in the online BSc? First year meaning like the foundation, right? Okay. Okay. So how many of you have already gone through, let's say, the machine learning foundations class? Okay. Okay. Thanks. So that helps. So what we are going to do today is, talk about this, very fundamental algorithm, which will lead us to solve a very practical application. We'll call this the eigenfaces. Some of this, for people who have already gone through the machine learning foundations, you might have seen the algorithm that we will talk about today. Nevertheless, I hope there will be something that will be new for all of you here. Okay, so we'll get started. So the title of the talk is Dimensionality Matters in Machine Learning, and we'll talk about what are called as eigenfaces. We'll learn what these things mean. If you have not heard of any of this before, that's fine. We'll start from ground up. So before we get actually started, one other question that I wanted to ask: how many of you have gone through a linear algebra course here? Okay, great. So that really helps. So I don't have to set up a lot of context. Most of you would know, would have this, sense of thinking about vectors and vector spaces and things like that. So we'll see how all of this will, beautifully connect themselves together to give us a very powerful tool, which is helpful in what is called as dimensionality reduction. We'll define all of these as we go along. So broadly, the learning objectives of today are going to be the following. So we are going to, develop intuition for a very, very fundamental algorithm in machine learning, statistics. It's an old algorithm. It has been there since the 50s, 1950s. Nevertheless, it's still, in some sense, the first go-to algorithm. If you are a computer scientist or a data scientist, we'll talk about this algorithm. I'm not going to let the cat out of the bag and say what this algorithm is. Some of you might have already guessed it, but for those who haven't, we'll see what this algorithm is as we go. The name is the last thing that we should talk about, right? So we'll understand the mathematics behind this algorithm. I think this is something that a lot of people kind of brush aside while developing intuition for algorithms in machine learning and data science. The mathematics is crucial, and given that most of you have seen some form of other linear algebra, so it will be like very easy for you to understand as well. So I hope to convince you of the power of linear algebra in data science through this algorithm. We'll finally see a very, very popular application of this algorithm, which is what we'll call as eigenfaces. As you can see, some faces here, weird looking ghostly faces. We'll see where these faces are important and what can we do with these faces. If time permits, we'll find out some issues about the algorithm. I think that's also, an extremely important part of design and analysis of algorithms in general in computer science, and more so in data science. To develop an algorithm, you need to understand, when would it work, when would it not work, what might be issues with the algorithm. We'll try to identify some. If time permits, we'll see how to fix these issues. That will lead us to a completely different path of learning something very, very fundamental in a lot of machine learning applications. We'll see. I'll at least give you a flavor of what kind of what these solving these issues would lead us to, right? So that depends on the time, right? So let's keep this as interactive as possible. I think the more we discuss, the idea is for all of you to learn something from this workshop. So some of you might take away, the whole mathematics ideas from the discussion that we'll have for the maybe next 1.5 hours. Some of you might at least get a geometric picture of some of the algorithms that you might have already seen. Some of you might just pick up some terms which you can go back later and dig deeper and understand. Anything is okay, but the more you interact, the more you will get from this workshop. So let's try to do that. Okay, so let's begin. So what we are going to do today is something in machine learning called as unsupervised learning. So has anybody here heard of this term unsupervised learning? Okay. Okay, so you have, I think both of you are getting to the same point. You have a bunch of points that you have. that's it, right? So you don't have any supervision. Typically, a machine learning task would involve supervision in the sense that, let's say I have a bunch of emails. Somebody might come and tell me, hey, these are the emails which are spam and these are the emails which are not spam, right? So there is some supervision there. Some teacher comes and tells you what emails are spam, which ones are not spam. And then your goal would be, typically in a machine learning problem, would be given a new email. Can you automatically figure out if it is spam or not? Right? So there is supervision involved, and you want to use this supervision to develop some algorithm which, given a new input, would predict the output. So that seems like a more scientifically well-defined problem. On the other hand, the problem that we want to look at today is where you don't have this supervision, right? So somebody just gives you a bunch of emails and tells you go figure out, right? So you have no clue what you want to do. So it's important for us to first, talk about, unless we are clear about what we want to do with the data, we won't be able to do anything, right? So we won't be able to go far. So in some sense, this is like an ill-posed problem, in the sense that you are not given a proper objective to deal with. So you don't know what you really want to achieve from data. You have to figure out what you want to achieve and then see how best you can achieve it, right? So we'll see what all these means as we go along. So there are multiple problems that one can look at in unsupervised learning itself. So I think one of you pointed out there is a problem called clustering or grouping, where you have a bunch of, let's say photos, and then you want to, group photos such that people, the photos in the same group maybe have the same person, right? So maybe that might be your objective, right? So in that case, you are kind of clustering photos into groups. That might be a problem that you may be interested in. There may be, the problem that we are going to be interested in today is even more, in some sense, fundamental, in the sense that this problem is called as representation learning. So there are two words here. One is representation and the other is learning. So we want to learn something from data, but what do we want to learn? We want to learn how to best represent data, right? So you are given a bunch of data points, and somehow vaguely we are asking a question, how to represent this set of data points that I have. So we need to make this more and more precise as we go along, and then we'll see what comes out of this. So here is what we want to understand, right? So at a very, very high level, this is the goal. So you are given a set of data points. You want to understand something useful about them, right? So this is a very vague statement, right? So this is an English statement, and that's where typically you start. You start from an English statement, and then you ask, which are the things that are vague here? First thing is, well, when I say data point, what do I mean by data point? Being linear algebra students, you might be already able to at least guess what do I mean by a data point. But then the other two terms are even more vague and fuzzy, right? So what do I mean by understand, right? So what do I want to understand? And the third thing is that, well, what do I mean by useful, right? So because there is no supervision, something that I will claim as useful may not really be useful for you, right? So we have to be clear about these things before we kind of develop an algorithmic sense for this. So if I had to ask you, so what would be your answer? So what do you think would be a way to say, I understand data? What are your guesses? So if I give you a bunch of points and then I tell you, understand something useful about it, what would that mean? Figures emerging from, okay. So all of you are saying patterns. In some sense, you are replacing one confusing word with another, right? So I'm saying you understand something from the data. You're saying maybe you're adding one word and saying you are understanding patterns from data. But what is patterns? So yeah. So okay. So that is one way to look at it. That takes us back to this grouping thing that we talked about, right? So you want to say that things that are similar to each other should be somehow grouped together. So that's one way to pose this problem also. So here we are going to think about a specific way to think about what do I mean by data points, what do I mean by understand, and what do I mean by useful. And here is how we are going to think about. The easy thing is say data points. Data points are just bunch of numbers, right? So each of you is a data point. If I am a machine learning data scientist, I treat people as points, right? So if I ask you a bunch of questions, you give me answers, your height, weight, whatever, age, right? So all of these things form you. Whatever I can talk about you is only about using the data that I collect from you. So data points are just a bunch of numbers. You can treat them as, let's say vectors in some dimensional space. In this particular example, I am collecting 3 numbers, height, weight and age. So every person here is a point in a 3-dimensional space. This point could be me, this point could be, and so on, right. So, this point in 3-dimensional space is represented using 3 numbers. So, that corresponds to a person. So, now once we have somehow converted this notion of data into numbers, now we can use all the tools and techniques, all the machinery that we have to understand numbers, to understand data itself. That is the whole point. And we kind of already have seen a lot of machinery here, right. So, all of you have seen linear algebra, which deals always with vectors, relationship with vectors, how do you transform vectors from one space to another. All of these things have been, you kind of might have seen earlier. So, we will see all of them will be useful now. So, that is the easy part. So, perhaps the more unspecified or unclear part is how do you define understand and useful. So, we'll take a particular in some sense a philosophical viewpoint to define what do I mean by understand and what do I mean by useful in this particular talk, and that is based on this running theme. This is not just for this particular talk. In general, as you learn more and more about machine learning, this would be a very useful way to think about what are you trying to learn, right. So, here is a famous computer scientist, also a philosopher. His name is George Chaitin. So, he says not necessarily with respect to machine learning, he generally says that you can claim that you have really understood something only if you can compress this information as best as possible, right. So, if I have to come back and explain an algorithm to you without really understanding the algorithm, right. So, I would not be able to, perhaps I will take much more time to explain an algorithm to you. On the other hand, if I have understood the algorithm, I can perhaps communicate my understanding in a much easier way. But what do I mean by I have understood the algorithm? I have kind of seen what is the structure in the algorithm. I have compressed that information and in my brain, and I store it in a compressed format. And whenever I asked, I can perhaps easily explain the algorithm to you. Again, all of this is very philosophical in nature, but then for us, this is a starting point. We somehow want to view understanding as compression, and this is a very powerful viewpoint in all of data science and machine learning. So, if you are able to compress data very well, then you can assume that you have kind of understood the data very well, right. So, we will see what compression means and how can we compress this, which means how can we understand data, and what are like useful more what is the use of compressing data. We will see all this in a minute, right. So, any thoughts or comments so far? This is all so far okay? Okay. So, let us go ahead and now make the problem a little bit more precise. So, you have a bunch of data points x1 to xn. So, if there are n people in this room, so each of you gets one data point x1 to xn. All of these are in RD. RD means each of you is characterized by d numbers, real numbers, and so each of you is a vector in some d-dimensional space, right. And then n of you are here, 150, let us say. And now what do you want to do? You want to output a compressed representation of this data set. Now we want to define what does compression mean, and then we will see how to do this compression. So, here is an example. So, let us say I give you these 4 data points, nothing to do with us here, but then generally 4 data points, and if I want to store this in a computer, there are 4 points, each point has 2 numbers, it is a vector in 2-dimensional space. So, I need 8 numbers to store these points. So, can you do better? For this set of 4 points, do you need to store, if you are a computer person, computer engineer, let us say, you would have to, let us say I ask you to store this data in a computer, right. So, do you need 8 memory units to store this data, or can you do better? We can do, are you saying yes or no? We can do 4? Okay, what is 4? What do you mean 4? The first value is x, the second value is 2x. So, that is a pattern that you are noticing in this data. So, how many numbers do you really need to store this then? 1 number for what? So, I need the entire data set to be stored, right. So, now naively you would need 8, but can you do better? And you are saying, yeah, you need 2. What are those 2 numbers? Right. So if okay, so you give me two numbers, and then using only those two numbers, can you reconstruct this entire data set? That's the question. 2 and 1. Okay, so if you just give me 2 and 1, let's say you give your friend 2 and 1, will your friend, does your friend have a method to reconstruct these 4 points? How? If you define a function, but then if I ask, let's say this is the height and weight of a particular person, and then somebody gives you just the two numbers which are 2 and 1, and now I come and ask you what is the height and weight of the first person, how would you get it? No, give me specific for this question, right? So the only thing, you have not seen this. What you have seen is the values 2 and 1. With just those values, would you be able to give this entire data set? Not, right? So yeah, so we need get back the matrix from the determinant. So 2 by 4 matrix, okay. For a 2 by 4 matrix? No, let's not think too hard. So it's easy. Yeah. 5, okay, good. Okay, so what he is saying is you don't need to store everything, you just need to store the first coordinate, and in this particular case, if you know how the second coordinate is related to the first coordinate, which is just a multiple by 2, then I will just give you the first coordinates and I will give you the number 2. Then the understanding between us is that, so whenever he gives me a bunch of numbers and a multiplier, and if you ask me for the third number, I will just take the third number, I will make that the first coordinate. To get the second coordinate, I will just use the multiplier, right. So that's a simple way to do this. So you can, you don't necessarily need 8 numbers here, right. So for the method that he uses, you just need like 5 numbers. Is that clear to everybody? Okay. So in this, so for a specific reason, we'll do it slightly differently. Most likely we'll use what you are saying, but then we'll do it slightly differently. We'll do it as follows, right. So we'll divide our data sets into 2 parts. In one part, we will call what is called as a representative of this data set. In this case, it is the vector 1, 2. It's a 2-dimensional vector. And now this representative is common for all data points. It kind of connects all the data points, the essential information in all these data points. Now for each of these data points, you just have a coefficient, right. So now if I have to get, let's say, x2, how would I get x2 from this representation? Yeah, so I'll take the representative which is common for all data points, I'll multiply it by the coefficient which is specific for this data point, and then if I multiply 2.5 by 1, 2, I get 2.55, which is my second point, right. So in this case, what I do is I have to store one representative for all of the data set, and for each of the point, I will have one number, right. So is that clear? Yeah, okay. So now we can essentially reconstruct the entire data set if we do this. I hope that everybody is convinced of that, right. Okay, so let's see this geometrically. You would have already seen this geometrically also. We'll come back to the geometric picture the whole of this workshop. So because it's easy to connect in pictures. So as you see in this picture, basically if I just plotted this point, they all lie on the line. That's what it means to say that the second coordinate is 2 times the first coordinate. It just means your slope is 2, right. So all of them lie on the line, which means that I have picked some representative on this line, and then everybody else is just some scaling of this representative. That's what it means, right. So essentially what I mean is, so here is a representative which we decided, which is 1, 1, 2, which is the point, this point, and then every other point is just a scaling of this representative, okay. Now notice that because of this geometric view, which is something also which is obvious, is also true, is that it is nothing special about 1, 2. I can pick any point along this line as my representative, and I will get a corresponding coefficient for each of the data points. For instance, instead of 1, 2, for whatever weird reason, let's say I want to use the representative as 1 over square root of 5, 2 over square root of 5. Now that is also okay, because now all the other points, because I am dividing the representative by square root of 5, all the other coordinates are going to get multiplied by square root of 5, right. So this is also a valid representation of this data set. Why would anyone want to pick this weird looking representative? We'll come to that later, but for the moment, just convince yourself that any point in this line is okay, right. Any questions here so far? Good. Okay. So the point is, originally you had, in this way of compressing things, originally I had 2n numbers because I had n data points, each data point was in a 2-dimensional space. So I had 2n numbers. Now after I do this compression, I only need n plus 2 numbers. Why n plus 2? The 2 numbers is for the representative, right. So in this case 1, 2, 2 numbers, and the n 1 for each data point. Now which is like, of course you won't really appreciate it when I say that instead of 8 numbers, I am storing only 6 numbers. That doesn't look like a big deal. But now you see that instead of, if you had a billion numbers, instead of storing 2 billion numbers, now you would only have to store billion plus 2, which is like almost a 50% reduction in the storage that you are doing, right. So as n becomes bigger and bigger, and of course we are all going to at some point become data scientists, we have to deal with big data, and so the more the reduction that you have, the better, right. So in some sense that's a useful thing. Okay, good. So anything so far? All fine? Yeah, is there a question? Okay, good. Okay, so what is this? Of course, this is what I meant. Any point along the yellow dotted line can be chosen as representative. Just keep this at the back of your mind. We'll come back to this later. Of course, not the trivial point 0, 0. If you choose 0, 0, then you're doomed because you cannot multiply and get anything else from that, right? So that's not allowed. Okay, good. So now real life is not so rosy. Nobody is going to give you big data where everything falls on a line, right. So even if I collect information of height and weight from people in this room and then I just plot it, they are not going to fall on a line, right. So though you might kind of expect like a relationship between height and weight, in some sense if height increases, you would expect the weight also to increase. On the other hand, if I just collect this information today, right now, and then plot it, of course they are not going to fall on the line, right. So there are people who are taller than the average, there are people who are heavier than the average, all sorts of people are there, right. So I might be an outlier here in this particular group also, right. So anyway, so that and we have to deal with this, right. So now let's say we have this extra point. So we had these 4 points lying along this line, and now I have this extra green point 5, 6. So now how do I compress this? Forget the black lines for the moment. So let's say I introduce this extra green point 5, 6. Now you have 5 points, not all of them lie on the line, 4 of them lie on the line, 1 point doesn't lie on the line. Can you compress this data? Okay, so he's saying you project it onto the line. We'll come to the projection part in a minute, but if I want like a lossless compression, right, so the reason why I did this is because now I can exactly get the data points here, right. So using fewer storage. Now can I do this here? So for these 5 points, is there a method, right? So perhaps some pattern that I am not noticing, maybe are you noticing, with which you can, maybe store lesser amount of data and still reconstruct? Each number, up and down numbers are same for these 4, but now you have this guy who is kind of screwing up your, this is upper number plus 1. So basically then you will have to look at each data point and do something specific for that data point. That doesn't sound like a practical solution, right? Especially when you have billion numbers, you don't want to go poking each number and seeing something, doing something. So now let's say imagine the case where you had billion points instead of just 4 points. So billion points lied along this line. This 1 point does not lie along this line. If you did not have that point, you would get 50% compression. Half a billion numbers are enough to be stored. But just because you have that 1 point, now you get 0% compression. You will have to store everything. That doesn't sound like a very nice thing to do, right? So you have to deal with it somehow. So how can we deal with this? Ignore. Okay, so that is that's the easiest thing. You're causing problem, throw it away, right? So yeah, so that's a good idea. That's a valid way to think about this. The problem though is that a priori you don't know whom to ignore, right? So you need to figure out which point is lie on the line and then do some ignoring, right? Yeah. Okay, good. So what she's saying is that, well, you can either ignore, or if you still want to use it somehow, you have to let go of this notion of, I will have to reconstruct the data set exactly. If you want to do reconstruction exactly, you need all information about all the data points, right? So you cannot really do compression. But then if you are okay to let go of some part of this data, in other words, if you can somehow, pretend that this green point, there are two things you can do. You can somehow pretend that this green point was not there at all, which is the ignoring part. Or what you can do is that you can pretend that this green point was not here. It was instead not here, but then it was actually on this line, right? So if you had to pretend that, right? So for example, I can pretend this green point is anywhere on this line, right? So maybe I can pretend this point was here, maybe this point was the origin. I mean, I am deciding to choose a point to, as a proxy for this green point. I can choose it anywhere, right? So, but where would you choose it? If you had to pretend, if you had to choose a proxy for the green point along the yellow line, shortest distance, why? What is error? Error, how are you defining error? Well, as you can see here, the error is, so the distance between your proxy and the original point, if it is as small as possible, then it means that you are not losing a lot, right? So in this case, if I pretend this green as this point, then I am losing this bit. If not, I am losing this bit if I am pretending it to be the origin. Both of these are lousy ideas, right? So maybe there's a better way to represent, find a proxy for this point, which is of course, as all of you say, is the shortest distance, right? So which means that you will actually pretend that this point is here, and now why would this shortest, okay, so I put this shortest distance point here, and then I'm saying this is the projection of the green point onto the yellow line, and I'm putting this, symbol here, which of course is the perpendicular symbol. So why is these two perpendicular? Why are these two perpendicular? Why? Yeah, why? Yeah, it's Pythagoras theorem. So I mean, you can easily argue, right? So there are multiple ways to argue this. We are not going to argue this, but so the shortest distance happens to be the perpendicular distance, right? So you just project it along this perpendicular direction to the yellow line, you will get this point, right? Okay, good. So now what we have done is, once we have identified this proxy for the green point along the yellow line, we are good to go. Now I can pretend that this is my data set and I will get 50% compression. What I lose is the reconstruction, right? So when I try to reconstruct this data set, there is nowhere, this green guy is out of picture. I should forget the green guy, right? So I'll only reconstruct the black guy and I should be okay with that, right? But in most cases, you're typically okay with that, because data is always inherently noisy, and this can be seen as a way to reduce noise. We'll build on these ideas as we go along, but so far are things okay? Any questions? Yeah, good. Okay. So here is what we'll do. So now I give you this green line, yellow line, and I give you this green point. I know that I need to find the perpendicular onto this yellow line, which is the black point. But what is that point, right? So we need to mathematically express that point to do any analysis, right? So for that, we need to first decide what is this, how are we representing this yellow line itself. Now we know that the yellow line can be represented by any representative along the yellow line. I can pick any representative that I wish, which means I can pick a representative which is of length 1. I mean, I can pick any point along the yellow line. We saw that, right? So, and that can be used to represent any point along the yellow line. I'll pick the one that has length 1. That will just make a lot of math convenient, right? So, length 1 means that W1 squared plus W2 squared equals 1, right? So, it is along this circle. That's all it means. Now, I ask the question, well, if I take a point x1, x2 and I want to find its representative proxy along the yellow line, which I am going to think of as, represented by this vector W1, W2, where does that black point fall? We know it's a perpendicular point, but how can we express that perpendicular point? Again, if you do some computation, so basically you can set this up as an optimization problem and all that. Again, we won't do that here. So, this turns out you can express this as some constant times W1, W2. It has to be some scaling of W1, W2, right? Why? Because it is on the yellow line. By definition, the black point is on the yellow line. So, every point on the yellow line is some number times W1, W2. So, this black point also should be some number times W1, W2. Till that it is easy to see. Which number is this? Well, that number will depend on x1, x2, because different points will project to different points, right? So, it has to depend on x1, x2. It has to depend on what your representative also is. Now, if you choose your representative as length 1, then this point has a very nice form, right? So, it has the form that this is x1 w1 plus x2 w2 into the vector w1 w2, right? So, remember this is a number, x1 w1 plus x2 w2 is a number which tells you how much you should scale the vector w1 w2 to get the black point, which is the projection of the green point onto the yellow line. Now, where have we seen this? All linear algebra students. What is this? x1 w1 plus x2 w2. Yeah, so for people who have already gone through some linear algebra, should be immediately obvious that this is in fact the definition of the dot product, right? So, the dot product of two vectors is just that you take one vector, project it along the other vector, right? So, if the vector that you are projecting it along is of unit length, then what you get is just the dot product, right? So, that is the geometric explanation of what a dot product is. Okay, good. So, what does this tell us? This tells us that basically if I give you an yellow line and I give you a point which is not on the yellow line, now you can find a proxy on the yellow line by just taking dot products. The dot product will give you the scaling. That is what this is so far saying, right? So, in general in high dimension the same thing happens. So, instead of x1 w1 plus x2 w2, you are going to have x1 w1 plus x1 w2 dot 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 till xd wd in d dimension, right? Everything else is the same. Good. So far okay? Any questions? Yeah. Yeah. So, our main aim to study is to figure out how to, so far our main aim is to figure out a way to compress data, right? So, compress means that our notion of compression is that if all the data points lied along a line, then I know, if all the data points lied along a line, then I know how to compress them because I have a representative and a scaling, right? So, now if the data points don't lie along the line, I still want to be able to compress them, right? So, now for that I need to understand where are these proxies for these points which are not on the line, and that we have so far found out, right? So, we will build on this, okay? Any other questions? So, this line is a straight line. In this particular example, I am assuming that all the points are in this line, one point is not on this line. Now, I can always decide to have a straight line, right? So, I can fix a straight line passing through the origin, and then I see that there is only one point which is not on this line. Now, your question is valid in the sense that who gives me this line, right? So, even if data points were lying along a line, but nobody is going to give me this line, or maybe the data points were not lying along the line at all, right? So, all sorts of things, crazy things can happen, right? So, here is a very, very simplified picture where all the data points were along the line, one point was not along the line, then we know what to do. Now, I have to tell you what this line is, I have to also tell you what this point is which is not on the line, then you will be able to do this. But then nobody is going to give us that, right? So, we are just given a bunch of data points and we need to deal with it. So, how do we do that, right? So, that is the immediate next question that comes up. right? So let's see that, right? So this is the natural question that all of you are asking, right? So given a line, we know how to find a proxy. But the question is, how do you find that line in the first place? Because all you have is data, right? So, you are always going to get points. You will never get points where just there is only one point which is not on the line, right? So, you are always going to get points all around the place. Again, let's look at the height weight example, right? So, you might have a linear relationship between height and weight, but that doesn't mean that, if I am particular height, then nature does not dictate that I have to be some scaled version of that weight, right? So, a lot of other factors dictate that, right? So, and so there is always this noise that you will have, but then there will still be an overall relationship that if your height increases, on an average your weight also is going to increase, right? So, that is the overall line, that is where the overall line comes from, right? So, we are assuming that there is a linear relationship, that is an assumption between the features that you have, and given this assumption, how can you, make that line precise? How can you find that line? That is the question, real question that we are asking. In other words, here is the goal, right? So, now what we are saying is that we want to develop a way to find a compressed representation of data where points not necessarily follow a line, right? So, now in this particular case, take this example. Now, imagine that there is no yellow line, there is no black dots, there are only the red points, right? So, you only have the red points. None of the red points fall on a line, right? So, you take any line whatsoever you want, none of the red points fall on a line, right? So, at max you can make two points, maybe even that is not possible in this case, especially if your line is passing through the origin. If you make one point fall on the line, none of the other points perhaps will fall on the line, right? So, this is not like an exception, right? So, this is the rule. You are never going to get points that neatly align itself, but still you need to deal with it. The question is, how do we do this? Well, of course, we know how to do this. In some sense, we have built the machinery, just that we have to, expand it to see what happens. What we can do is that it's not necessary, but if we will see why. So, in some time we'll see that if you so there are different ways to fix if you don't assume that points necessarily pass through the origin. I'll come to that point. Hold on to that. Yeah. But what can we do now? So, our goal is the following now, right? So, I am given a bunch of data points. I need to find a line such that this line, in some sense is a good line. In other words, if I find proxies for all the data points along this line, I don't lose much, right? So, for example, for this data set, if for each point, red point, the proxy is the corresponding projection, black point, and what I lose are these blue bits, right? So, now I can pick any line whatsoever I want and say that, hey, this is the line that best represents this data. But then once you fix a line, the data set will tell you how much you are losing by, projecting onto this line, right? So, now what would be then a goal? The goal would be then to find a line which kind of best represents the data, whatever that notion of best is, which we want to now build. Of course, we somehow want to say that these blue bits are not too big, right? Smaller the blue bits, the better. Now, if it so happens that there is all the data points did lie along a line, then that line will indeed should be the best line, right? So, because there are no blue bits, the points themselves are their projections. You don't need any proxy for them, right? So, now we need to set up a way to find out this line, right? So, that's the immediate goal for the moment, right? So, let's see how we can. Before that, any questions? So, what you are saying is, so let's say this point is the red has its proxy here. Maybe you had a red here itself. Is that what you are saying? Well, for that red, it will be its own proxy. Now, so if it is along this direction, then this will also get projected to the same black point. Yeah, so that is what would happen, right? So, in fact, you can have a lot of points along this line. That depends on how many points you have, right? So, if you have 1,000 points along this direction, maybe this is not the best line. Maybe some other line would be the best. We are going to lose, right? So, there is nothing special about 2 points projecting to a same point. That's what I'm saying, right? So, the moment you project it, you are losing, right? So, there is nothing special that the projections align. There is nothing special about that. Yeah. Any other questions? Good. So, now let's try to set this up as a problem which we want to solve of finding the best line, right? So, because nobody is giving us the line, we need to find this line, right? So, here is the formal problem that we want to solve. So, given the data set, you want to find the line that has the least reconstruction error. That's just a technical way of saying that you want to, the blue bits, the length of the blue bits should be as small as possible, right. So that's what I mean by least reconstruction error. So we know, remind yourselves that we know that if I take a point x and then I project it along the direction of w, where w's length is 1, then that point that I get is x transpose w times w, right. So that is the projection. Now the error itself can be written as what? Now again, simple vector algebra would tell you that if I add the black vector, which is the vector from the origin to the black point, plus the blue would give me the green, right. So that's how you add vectors, right, tail to head, head to tail, right. So that's how vector addition happens. So which means that the blue itself is a vector, which is this vector, right. So the one that goes from origin along this direction for this magnitude. So this blue error bit is exactly the vector x minus x transpose w into w, right. Because if I add this to x transpose w into w, I get x, right. So this simple vector algebra. So is this clear why this is here? I mean, some people typically have seen students getting confused as to why did I put it here when the blue is here. Why is that? So I want to know what is this error bit, error piece, right. I am saying the error is a vector, but then it's not this, it's actually this vector. Why am I saying that? Yeah, by vectors, by definition, point from the origin, right. So that's how you think of vectors as, right. So this is basically, you look at the parallel vector that starts from the origin. Okay, good. So now what is our goal? Our goal is the following, right. So we are given a data set that's given to us. We want to find a line. I have infinite choices of lines. I can pick whatever line that I want. Now once I fix a line, I get a specified, mathematically precise way of defining how good this line is, right. So this line for this data set is, the goodness of this line for the data set is defined as follows. For each data point, you see how good is this line, and then you add up the goodnesses, right. So or you add up the errors, right. So the error being high would say that that line is a lousy line. The error being low would say that the line is a good line. Now what is this error? We are going to think of this error as simply the length of this blue bits, right. So the length of the pieces that you are actually missing by assuming proxies for your data points. So what would be the length of this blue bit? How would you define the length of a vector? What is the magnitude of a vector? Norm. What is norm? So there are multiple ways you can give different names, but then I won't be convinced. I mean, how can I program it? You have to tell me the equation. So let's say you have a vector a, b. What is the length of this vector? Okay, good. Square root of a square plus b square. Why? Because a along the x-axis, b along the y-axis. So this is the vector. Pythagoras theorem. This length squared is a squared plus b squared. So this length will be square root of a squared plus b squared. I'm sure all of you understand that, right? Okay. So which means that in our particular case, we want a length of the blue bits, which is, you can either look at length or length squared. Doesn't really matter. Both of them are positive quantities. So you can look at both. So let's say I define my error as the sum over all data points, the error of a particular line which is determined by a w, right. So for a given point xi, right. So I have x1, x2 till xn. So the point, how do I find that? Let's say I pick one point xi. Now I want to know the blue bits, the vector corresponding to the blue bit for this point xi, right. So that would be xi minus xi transpose w into w, right. So because that is what we said is this error vector. Now I look at its length squared. Of course, I know how to calculate length squared. Length squared is just, a squared plus b squared, or you can also write it as in terms of dot product notation. A vector's dot product with itself is just its length squared. A, b is the vector, you dot product with itself, that would be a squared plus b squared, right. So that would also be the length squared. Anyway, if the equations are overwhelming you, don't worry about it. The idea is more important. We are just taking a line, projecting the data points along this line, looking at the pieces that we miss, and then sum up their length, right. So now what would this give me? This would give me how good a line is for this data set. Now what do I want to do with this? What is my goal? I want to find that line that is as best as possible, right? So, which means that I need to find a line which has the minimum error, which means my goal is now very precise. I need to minimize over W over all possible lines, but then every line can be, you can choose a representative of length 1 for that line, which means that W transpose W is 1. Among all possible choices of W, there are infinite possible, uncountably infinite possibilities. You want to find that W such that if I take each data point and look at its proxy on this W and measure the missing bits, the pieces that I lose, and then I sum them up. Maybe you want to divide it or you don't want to divide it, doesn't really matter. You want to find the W which has as small a value as possible. So, this is the problem that we want to solve, right. So, now this is a very specific problem. We can ask how to solve this and so on, we will see that. But from nowhere, we have now identified a problem that we really want to solve, right. So, now the question is what does this solving this problem teach us and so on. We will talk about that, but is the optimization objective clear? At least intuitively it is clear if you are not maybe immediately following the equations. I hope at least it's intuitively clear what we are trying to do. Okay, good. Okay, so we want to solve this, right. So, I mean, now we need to find the W. So, let us just understand what will you do if you find the W. Let us say you found the W, then what? Now, even for this data, let us say we want to compress, that is the goal with which we started. I have data points, right. So, I collect all the data points x1 to xn from this class, height, weight. I have now found a line. By solving this equation, somehow I have magically found a W. Now, what do we do? Yeah, so the best fit line in this notion of fitness is W. I give you the W, right. So, I solve this problem and give you the W. What will you do now? Exactly, right. So, what is the scaling? What is the scaling corresponding to xi? It is just xi transpose W, right. So, what is the scaling? This is the point, right. So, this is x transpose W times W. The scaling is exactly x transpose W, which means for every data point, you just have to store x transpose W, one number, right. And then you store W itself, right. So, which comes out of solving this equation, right. So, now W is, so let us say you are in some high dimensional space, your data is not just height and weight. I collect 1000 information from each of you. So, each of you is a point in 1000 dimensional space. Now, I am finding a line that best fits this data in this sense of fitness. So, now that line is given by some W which is in this 1000 dimensional space. Now, for each of you, I will take your 1000 dimensional point, project it onto that line. I know that it will be some scaling of W and that scaling is given by xi transpose W. So, each of you will become one number. You were 1000 numbers before, now you have become one number, right. So, I am compressing your information of 1000 numbers into single number. Does that make sense? Okay, good. So, just so that we do not lose context. Okay, so few moments later, if you solve this equation, which I am not going to do because we do not have time, well, a few algebraic moments later, this will become like this, right. So, let us not worry about this for the moment. What this means is that you can equivalently solve this problem or you can solve a different problem. Let us not worry about what this problem is for the moment. All I want you to keep this in the back of your mind that there are two different problems you can solve to get the exact same W. It is just some algebra which I do not want to bore you with at this point, right. But then this problem has some nice, I mean not nice, but maybe nice, but a different way of looking at things. We will come to this after some time. But for the moment, the takeaway is that you wanted to solve this problem, you can also solve a different problem. We will come to what these problems are after some time. Okay, so far, so this is where we are, right. So, part 1 over. Given, just a minute, I will summarize this. Given a set of points, we know how to find a direction W where, well, that minimizes the reconstruction error. We know meaning, we know what problem will solve it. Let us assume for the moment that somebody will give you the solution to that minimization or maximization problem. The question is, well, are we done? Is this W sacrosanct? Are we done? I mean, can we do better? These are things that we need to ask, but before that, what's your questions? It's the same thing. So you had billion numbers, but each of those billion numbers had two numbers, right? So each of those billion points had two numbers. Now what we did was we changed the two numbers into one number. That's why you got the 50% reduction. So here we are exactly saying the same thing, right? So instead of two numbers, if you had billion numbers, if this class was billion sized class and each of you had a representation in 1000 dimension, still I am saying if I find a line, I am just going to reduce you into one dimension. I still have to store one number for each of the billion people, right? So, but then I just have to store one number. I don't have to store 1000 numbers. There I did not have to store two numbers for each of you. Now here I don't want to store 1000, I will just store one, right? It's a good thing or a bad thing is a different thing. We'll talk about it. Yeah. Yes, but then we agreed so far that this combination is the one that will give you the least error. There are different combinations, right? I totally agree. But then if you are forced to represent each of the person by only one number instead of 1000 numbers, then this is the best you can do. Now what you are asking is, maybe I don't need to reduce drastically from 1000 to 1, right? Is that what you are asking? Well, that would be one of the W's, right? So each W is giving you some combination of these height, weight and age, right? So what is X transpose W? X1 into W1 plus X2 into W2 plus X3 into W3. Height into W1 plus weight into W2 plus age into W3. Now if you solve this problem, you are finding that combination of height, weight and age that gives you the best, right? So among all possible combinations, that's taken care of. Is that clear? Any other questions? Yeah. You are right, we are projecting it to the best subspace, but then you have to quantify the subspace. It's not any subspace, it's a one-dimensional subspace, right? So if you are a linear algebra enthusiast, you would instead not say this as finding the best line, you would say that I am projecting my data points onto a one-dimensional subspace, and it's exactly what we did, right? So throw away the blue bits. That's how I would like to say it. But then if you are a linear algebra person, you would say it that. Both are exactly the same. Okay, let's move on, right? So let's try to identify some issues with this. So now let's move from two-dimensional data points, simple things that we are seeing, to three-dimensional data points. So let's say here is an example of three-dimensional data. Are you able to spot any patterns in this data? Well, take a look at this data. Does it? Okay, somehow you are seeing that it's lying along the same plane, but okay, good. You will have to look at it from different angles. I have only one slide though, so I don't have that moving thing. But yeah, so you are right. But what would we do, right? So that's the point, right? So we don't know what to do. So we will solve the equation that whatever we set up to find one line where you can project things to get the best line, right? So if I do that, let's say I get this line. This line passes through the origin. Now what I am saying is that this whole data set is best represented by this line. That's what I am essentially saying, right? So basically now what I will do then is I will project each of the points onto this line, and then I will only pretend that all the points are along this line, right? So this green line is what the method that we are developing so far is giving us as output. The question is, it's a good line or not? Is there something better we can do? Now, as somebody magically found out, right? So these points actually lie on a plane, right? Who said that? I think you should talk to the NPTEL coordinators and get a prize for that, right? So anyway, but good, right? So these points indeed lie on a plane, right? So what are we saying now? The points were all on a plane. That's the essential structure you have. But we are saying we are going to pretend that the points are on a line. Why? Well, that's how we set up our problem. We went out to identify the line where if you project your points, you lose the least. Still, if you look for one line, this is indeed the line that will give you the answer, right? So what would you do now? Once you know that this is in a plane, well, even if you know or not, now this is the line along the plane which you think is the best representative for this set of data points. Now, what does that mean? That means that you have all these bits, right? So, I am not drawing it for everything, but then only for some data points. Here are these bits that you are missing, right? Now, what can you say about these bits that you are missing? So, meaning what can you say about, so I am drawing it only for these points, but then every point you can imagine you have to project it onto the green line, right? So, but then if you take a look at, careful look at these purple things, where are they? They are on the same plane. Why is that? You are right, but why? As simple as that, right? So, the lines, imagine all the points were on the floor, right? So, and then I decide to find a line that on the floor that best fits the points. Now, the remaining points, the bits, the projections will also lie along the floor, right? So, they cannot suddenly climb up, right? So, because you are looking for the least distance, right? So, they will also be on the floor, right? So, which means that if I say they are not only on the floor, they are also in the direction which is perpendicular to this green line. Why? Because you are projecting it along the direction perpendicular to the green line. Where else can they be? They will all align up in the same direction, right? So, now the question comes, should we treat this data, these three-dimensional data, as if I can represent each data point with one number, or would I need maybe two numbers? Because it looks like these bits, right? So, they are not insignificant. The structure is not a line, the data is not really on a line, the data is actually on a plane, which means that you would need more numbers to represent data. You do not necessarily need all three, because the z coordinate is 0, at least in this case, right. So, there is one dimension which is useless, but then there are two dimensions which have information, but then we are only using one dimension. Now, how would we change? I mean, we already have an algorithm which will give you a line. Now, we can either throw that away, or we can ask, can we do something better with whatever we have? How would you, what would be the first thing that you would think of? Yeah, try to project both the axes. Well, in this particular case, it so happens that I have drawn this along the floor. Maybe it's along this direction, right? So, you cannot project it along axis and find which is best, right? So okay, so I want you to think about what structure are you finding in these bits, right? So, the conclusion that we are drawing is that these bits are not noise. These bits have information, right? So, they are also part of your data. You cannot simply throw them away, right? So, because they participate in, I mean, providing you some information about the structure in this data, which in this case is that the data is all in the same plane, right? So, what can we do? Yeah, good. So, what he is saying is that, I will slightly rephrase what you are saying. So, he is saying that, well, you observe that the projections are all in the perpendicular direction to the original line that you have found, and you want to find out some information about the bits, the blue bits themselves. So, now what you can do is, I can now run the same algorithm not on the original data, but on the blue bits, right. So, I can convert my data set into a different data set, where each data point would correspond to now the blue bit, the residue vector, the error vector, whatever you are treating them as error vector, but they might have information. Now, I can construct a new data set, and now I can find a line for that new data set. Can I do that? So, does it make sense why that might be a okay thing to do, right? Yeah. Direction also, yeah, they do, right. So, because this point, can be got by origin to this vector plus upward vector, right. So, I mean, rather the y axis in this direction, whereas this would have a different direction, right. So, they have direction, it is a vector, by definition it has a direction, right. Yeah. Okay, so here is the idea, right. So, you do the following, you have data set in d dimension, 1000 dimension, you find w using our method, that whatever we did already. Now, your x now becomes x transpose w into w, because you are pretending all points are lying along this w, and for each point the scaling is given by x transpose w. So far we agree. Now, what we do is, we compute the blue bits, which are just the residue. which is you remove this component from x, right. So, what remains is x minus x transpose w into w. What we are positing is that this also has information. This is not just noise that you can throw away, which means you can potentially come up with a simple algorithm which can do the following, right. So, you start with the data set, find the first line which you will call as W1. Now, find the projections onto this line W1. With respect to W1, you just need to store x transpose W1. Now, you take the remaining and then create a new data set, run the same algorithm again. Find the second line, call it W2. Now, it might so happen that even after you found W2, if you are in 1000 dimension, remember W2 is a different way of combining, right. So, you asked about combinations. So, originally we had one way of combining height, weight and other features, which was the best way to combine if you are allowed to combine in only one way. But now, if you are given two ways to combine, the first way you have gotten already. Now, there is a different way to combine height and weight that will also give you some information in the data, right. So, and you can keep on going as long as you want. Now, how many, when you say as long as you want, how long can you go? How many lines can you find at max? What do you mean closest to the original one? Okay, so original data is in 1000 dimension. Now, how many lines can I find at max? Number of data points? Number of dimensions. Okay, good. So, what happens? Let's say you are in 1000 dimension. What happens after you find, maybe 1000 is too hard to visualize. Let's say we are in 3 dimension. I found one line, I found the remaining residue, I again fit it. I found one more line, I again found the residues, I again fit it. I found the third line. Well, why can't I find the fourth line? What stops me from finding the fourth line? Okay, okay. So, two people have said this. I am wondering why. So you are saying after the third iteration, again the data points will become x1. Why? Because every round you are removing something, right? So, basically, initially you had x. Now, you removed x transpose w into w1 from it. The next round you will remove x transpose w2 into w2 from it, and you will keep removing. Now, I am saying after d times removing, what will you be left with? What will be your residues? Okay, so let me ask it differently. Let's say initially you started with a data set in 3 dimension, but then all the data points were along the same line. Let's say you got lucky. Let's say all the data points were in the same line. Now, if you find W, that line you would be able to find that line, obviously, right? So, now what would be your blue bits? All of them will be 0, right? So, if all of them are 0, then there is no point in going further. Now, what I am saying is that if you do not have 0, then you can go one step further, but then after the number of dimension steps, they will become 0, right. So, because you have extracted all information from the data, so you will not be able to, you do not have to necessarily move after that, right. So, but now let us ask the other question, right. So, should I really go till d dimension? If I have 1000 dimension, I can go till 1000 dimension. After that, the residues all become 0 and useless. But do I really need to go till 1000 dimension? When will I stop? This is an engineering question. There is no mathematical answer to this, perhaps, right. So, if you had to do this, when will you stop? Yeah, so when we feel it's good enough, we will stop. But it should be good enough for everybody, right. So, like, what is a way to say good enough? You're right. What does good enough mean? Okay, somehow you need to look at the blue bits at that stage, and then if they don't sum up to too large a value, then you can stop, right. So, we will discuss maybe if time permits how to do that, but then this is the general idea, right. So, at some point you decide that the remaining pieces are actually error, and then I stop there. Let us say I stop after 10 rounds. Now what? How will I, what all have I stored? I have gotten W1, W2, W3 till W10. I have run this algorithm 10 times, so I have 10 lines. Now, for each of these lines, I have the projections of the data points onto these lines. I have X transpose W1, X transpose W2 till X transpose W10. So, the original 1000 dimensional vector, now I am representing using 10 numbers which are X transpose W1, X transpose W2 till X transpose W10. Earlier I was just using one number, X transpose W only. Now I am representing using 10 dot products. So, every point is represented using 10 numbers, not 1000. But then I also have 10 representatives now, because if I have to reconstruct this data point or the best version of this data point, what will I do? I will first take X transpose W1, scale it with that vector W1 plus X transpose W2, scale it with W2 dot 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 X transpose W10, scale it with W10, and that would be my best representative for this original data point, right? So this is this clear so far? Okay, good. Okay, so now we will come to this question that was asked: should lines pass through origin? Because if I have data like this, let's say, right? So this is just an aside. We just have to make sure that we are not doing some silly mistakes when we are developing this algorithm. Let's say my data was like this. Now I am trying to find I'll take each line and then project it along those lines and see where the bits the remaining error bits have the smallest length, right? So now if this is my set of data, now I have three choices. Let's say the x axis itself is a line, y axis is a line, and this x equal to y is a line, right? So if I project it along x axis, then I get all these green bits. If I project it along y axis, I get these blue bits. If I project it along the x equal to y line, I get all these gray bits. Now in this case, it might so happen that if your data is like further away from the origin, these green bits might actually sum up to a lesser value than these gray bits. You can see this data and you realize that the relation is actually linear, should be actually captured using the x equal to y line. On the other hand, the way we have set up the problem, which is just the length of the bits, the remaining bits, it should so happen that the x axis might be a better line in this case. How can we fix this problem? We can either consider a line which is not passing through origin, or there is an alternate way to fix this also. Consider which as x axis? No, you still have these points. If you consider this itself, I mean basically this line is not good, right? So that's what we are saying. One way to say is that I won't only search for lines passing through the origin, I will search for lines which don't pass through origin also, right? So that's one way to solve this problem. A simpler way to solve this problem, which is typically used in practice, is you will center the data, right? So the problem is because the data is away from the center, right? So all our lines pass through origin. So we somehow want our data to be spread around the origin, and to do that, what you can simply do is shift the origin, right? So you will simply say that, well, my origin is not here, but then my origin is here. In other words, I will bring the data points, move the data points such that it's the center of the data points is actually the origin. How can I do that? Yeah. So you take every data point, you have 100 data points, you find the mean of the data points and subtract the mean from each of the data points. Right now you get a new data set. For this new data set, if you take the mean, because you have subtracted the mean from each of the data points, the mean of the mean subtracted data set would be the origin, right? So basically, geometrically, it means that like I am pulling these guys and then putting it here. That's all, right? So now I can search for lines passing through origin, right? So that's one thing to keep in mind. So now this is our new algorithm for this problem, which is I have this input data set, I do data centering so that the data is around the origin. I will find the first best line, whatever best we defined earlier, and now I replace the data set with its residue, and I will do the next line, I will keep going. I will stop when we feel it is good enough, meaning if the residues are not too large, then I will stop. This is a simple algorithm. What have we gained? Well, why do we do this? If we actually had to, go till d equals 1000, if I had to store 1000 lines, then there is no real savings that I am getting, right? So because every data point was originally in 1000 dimension, now I am projecting it on 1000 lines and then storing 1000 numbers. What's the big deal, right? So I am not saving anything at all by doing that. Now what we are saying is that if it so happens that you don't have to go till 1000, but then in between, maybe after 10, if you realize that well, whatever the missing pieces, the remaining pieces are not too long, right? So their length is too small, then I can only store it using 10 numbers. I can ignore the rest, right? So that's a big savings, because now instead of 1000 dimensional data points, you have done a dimensionality reduction and represented the data in a low dimensional space, right? So subspace, if you will, right? So that's where you kind of gain a lot, right? So either the residues become 0 much earlier, in which case the data is actually on a, let's say, a 10 dimensional subspace of the original space, or maybe it's a plane in 3 dimension, maybe it's actually on that, or maybe it's on the plane but then slightly up and down on the plane. That's still, there is no plane that kind of completely captures the data. Still the error with respect to this plane is too small that you can kind of pretend as if the data points are on the plane. In which case you don't have 3 numbers to store the data points, 2 is enough. In practice, I mean, natural real life data often tend to live in some low dimensional space, and so this is a very, very powerful method. So this method has a name. I don't know how many of you have heard this. How many of you had heard this name before coming here? Okay, some of you. Okay, good. Yeah, so this method is called, for whatever reason, it's called the principal component analysis. This was developed from the 1950s. So it's called principal component analysis because these W's that you find on each of these rounds, they are called as principal components, right? So that's what that's where the name principal components comes from. Analysis is just to make the algorithm look fancier. That's all. Okay, good. So to get some perspective, if you had n data points in d dimension, in the uncompressed way, you would store n into d numbers. But now, if you just store them in 3 dimension, let's say, then you would need 3 representatives, each in d dimension, for which you need 3D numbers. And for each data point, instead of d dimensional vectors, you only need 3 dimensional vectors. So there are 3n numbers. So the total numbers you would have to store is not d into n, but just 3 into n plus d into 3, which is much, much lesser than d into n, especially if d is large, right? Okay, any questions about the algorithm itself? We'll see some more nice views of this algorithm and then we'll get to our promised the ghost face applications. Yeah, any questions so far? Okay, so now we'll look at, yeah. Okay, so the question is, in real world, if you do PCA, you might lose a lot of information. So is there a hard and fast rule that we should do PCA in real world data? The answer is no, right? So it is not that this is like a must to do, right? So, but then this is the first thing you should try. If it so happens that, you know, if you do this and then you figure out that instead of 1000 dimension, with 10 dimensions you can actually represent the data without much loss, then it will work wonders, right? So you should actually do this, and we'll see an example where it might happen. But there might be cases where it may not be useful also, right? So you should look at the residues and then decide on it. Yeah. Why is there 3? This 3 or this 3? The first one? Okay, so I have found 3 lines. So each line is in d dimension. So in this particular case, if I want to represent the data in 3 dimension, then I am saying you would need 3d plus 3n. If I want to represent in some k dimension, I would need kd plus kn. Right? So that's what it is. It depends on the data. It does not depend on the algorithm. Right? So essentially you are looking, so if I set d equals 2, then it means that I am looking for planes. If your data lies on some plane, then you will get a lossless reconstruction. The residue will become 0 much earlier, right? So if you want to reduce the dimension and still want the property of losslessness, then the only way that can happen is if indeed your data was in some low dimension. If not, you are going to suffer some loss. But the loss will be minimal, and in general, it's a good practice to remove that loss if the loss is small, because removing that loss might actually help you if you are using these low dimensional features for some other downstream applications, right? So there is a statistical learning theory aspect of why you should do this, but let's not get into it. Let me just say that it's a good idea to do that, even if the loss is not 0. Yeah, is there a question? Okay, good. So now we'll understand it in a different way, so that So basically the idea is we have an algorithm, we know what it does, right? So we can stop there and say that this algorithm works in practice and go home, or we can try to get more intuitions about this algorithm by looking at it in different perspectives, right? So that's a good thing to do always. You have something which works, you want to kind of go into detail and then understand it from different directions, and each of these directions might actually give you a new insight about what is happening in the data itself, right? So what we will do is we look at a slightly different viewpoint of the same algorithm, exact same algorithm. Now remember, we had this minimization problem which we also wrote as a maximization problem. We'll try to understand that maximization problem a bit more. The minimization problem was easy to understand. You are just doing error minimization. You know which lines, fix a line, project it, find the error bits. That was our motivation, right? The maximization problem we don't know what is. I mean, we didn't even talk about that problem. We'll take a closer look at that problem and see what comes out of that, right? So this is what we started, right? So you wanted to minimize error. This was our original problem, which is sum over xi minus xi transpose w into w. This is my representative along w. This is the error of the remaining piece. I take the sum over all data points. Things are easy. Now I am saying you can also treat this as what is called as this maximizing variance viewpoint, which is like you can also look at it as a maximization problem of a different objective, where you have this w transpose cw, where C is actually a matrix of this form. The form of the matrix is not really relevant now. If you are already able to see why this is a covariance matrix, good, right? So you will probably be able to follow it faster, but then for those who are not seeing it, it's okay. So it's not important what the form of the matrix is, but then just let's imagine that there is some matrix here, right? So what is this exactly telling us is that the data's dependency now comes via this matrix only, right? So that's an interesting observation here, right? So I have data x1 to xn. Each of this is in some 1000 dimensional space. What I'm really saying is that, well, I can get exactly the same w by maximizing w transpose cw, where C is some matrix, which means the entire data's relationship comes via this matrix only. If I know this matrix, if somebody did not even give me the data points, but just gave me this matrix, I'll still be able to find the w line. So there should be something special about this matrix, right? So let's try to understand what this matrix is and what is so special about this matrix, right? So, this is what is called as the variance maximization view, and let's see what this does, right? So towards this, what we want to really understand is, which direction is this w that we are actually getting is pointing given the data. Let's try to understand it this way, right? So let's say I have a bunch of w, w1, w2, w3. Now all of these are in the unit circle, right? So their lengths are 1. Now here is some matrix C. Now if I multiply this, apply this C to this vectors in the unit circle, where will they end up? So let's say I take every point in this dot, every vector in the circle, and then I apply a matrix C, and then see where do they end up? Where will they end up? It depends on C, some property of C, but in general, can you comment anything about the shape? C is a matrix. So it's not x transpose x, it is x transpose. So it's a matrix. It's a sum of n one dimensional, rank 1 matrices. Yeah. It will be parallel to what? C is a matrix, right? So I'm saying I have w1, w2, w3. I now want to plot C times w1, C times w2, and C times w3, and I'm asking where are they? It will be another circle, is what he's saying. That's like the meme that we saw in the morning. But yeah, okay. No, I should be very careful. Yeah. Anyway, you guys are not in the video, but yeah, some rotation will happen. Okay. So interestingly, if you apply C to every point on this circle and see where you end up in, you will end up in an ellipse, right? So basically what this means is that each of these points goes to some point in the ellipse, right? So of course not for all C's, but then for the C's that you actually derive from data in this form, right? So why is this useful? So what are we trying to ask now? So let me show this picture and then we'll see what we are asking for. Right. So what I'm doing is that I'm moving my blue vector and then I'm plotting the corresponding, C times W vector, right. So as the blue vector traces the circle, you can see that the yellow vector, which is C times the blue vector, is kind of tracing the ellipse, right. So it will kind of completely trace the ellipse. And now also look at the lengths of the blue vector and the yellow vector and the directions in which they are pointing, right. So at this point now, right now, they are aligned in the same direction. Now as I go further, the length reduces and the alignment changes. Now after some point, they'll again start aligning to each other, right. So right now, right. So I think I missed that. I mean, between these 2 points, they aligned again, right. So there are how many places will they align when I take one full circle? 4 places they'll align, right. So where are those 4 places? So where are those 4 directions with respect to the ellipse itself? The major and the minor axis of the ellipse, right. So they will once align in the major axis, they will once align in the minor axis. Now what do we care about, right. So this is what is happening when you apply C. What do we care about? We want to find that W such that W's dot product with C times W is as high as possible, right. So we want to find such a W. Now if I tell you that for this circle you get an ellipse and now I ask the question which W, right. So I take some blue vector W and then I look at its corresponding yellow C times W and I ask when will this dot product be as high as possible? Where would that happen? What would be your guess? Okay, let's see, right. So this is, so these are 3 particular examples, 3 particular points on the circle, W1, W2 and W3 and they are corresponding CW1, CW2, CW3, right. So now let's look at W1's example, right. So this is W1, this is CW1, right. So one is in the circle, one is in the ellipse. Now what do I want to compute? I want to ask the question, is this the solution to the original problem, which is W transpose CW? Does it have the maximum value? Which means what should I compute? I should compute the dot product of these 2 vectors. But I know how to compute the dot product of these 2 vectors, right. So W is a unit vector, its length is 1. What is the dot product? The dot product is just the projection of C times W onto W. We saw that earlier, right. So which means that I can look at this line spanned by W and then I can project this and then this point is just W1 transpose C times W1 times W, right. So why is this quantity? This is, you take this and then dot product with this, that is just W1 transpose C W1 times W1, right. So this is scaling W1 by a quantity which is W1 transpose CW, which is exactly the quantity that we cared about here, right. So we want to ask which quantity, which W will give me the maximum of this quantity. In other words, we are asking in which direction should I find the W such that if I project CW onto W, right, so I get the maximum value. Is it this or is it this? Now here is a direction W2 which is actually aligning, right. So in this direction, if I have W2 and then I have a CW2, they are both in the same direction and in fact this is the major axis of the ellipse also, right. So now what is the projection of CW2 onto the direction of W2? Well, that's exactly on CW2 itself, right, which means CW2 can also be written as W2 transpose CW2, which is the projection of CW2 on W2, that scalar times W2. Now they are aligning, right. So now when these align, what kind of an equation is this for the linear algebra folks? What vector is this? So you have an equation where CW2 equals some scalar times W2. Yeah. So what does this tell us? This tells us that W2 is in fact the eigen direction of C. If you have not seen eigenvectors, so you can imagine that this is the direction which is the major axis of the ellipse that you get from C, and that major axis is exactly where you will have this maximum value. Why maximum? Because that needs a proof, but then why maximum? Because here in every other direction you are losing a piece. You will lose a piece, right? So here you won't lose a piece. Of course, you can also get the minimum using this, right? So here W3 is another direction where things align. We saw it aligns in 4 directions, 4 points, but then effectively only 2 directions, right? So the major axis and the minor axis. In the minor axis also it aligns, but then the length actually reduces, right? So from the circle, the ellipse is inside, whereas here from the circle, the ellipse is outside, and we wanted to maximize this. The question is, which direction does it get maximum? It so happens that this is in fact the the eigen direction of the covariance matrix, right? So so what we are essentially saying now is that, well, I can also think of this W that I am going to get as the direction of the major axis of the matrix, of the ellipse formed by the matrix given by C, which is the covariance matrix. But then that is, that is not really, that's okay. So that is for the linear algebra folks, right? So they should be excited that your eigenvalues come into picture here. But then for us, right, so more practically tell me something in terms of data points. I know you're asking that, right? So of course it's an eigenvalue. This value is actually the eigenvalue, the highest eigenvalue of the matrix C. That's what we are saying. But what is this value, right? So okay, so let it be the eigenvalue. Who cares? But then how should I interpret this value, right? So if you ask that, well, the interpretation is that this eigenvalue actually represents something very, very fundamental, right? So it is actually in this case the variance of the lengths of the data points after you project. Let me say that again. You have these data points initially. Think of this, look at the left picture. You have these green data points, and now I am finding these proxies along the yellow line, which are given by these black points. Now these black points have certain lengths, right? So this point has some length, not the residual length, this black point's length itself, right? So this has length till here, this has a longer, this is longer, and this is longer, right? So now what is the variance? What is the definition of variance? I'm sure all of you are aware, right? Stats 1, stats 2, whatever, right? So you must have seen this. Variance is just spread of data, right? So what I'm looking for the variance is, the variance of the lengths after I project it along a particular line. Now here are two possibilities, right? So one is I can project the data points along this yellow line, or I can project it along the blue line. Now after I project, if I want to see how much variance are there in this projected line, projected lengths, which one has higher variance? Is it the yellow or the blue? Why? What do you mean by variance? So I give you two set of numbers, 1, 1, 1, 1. This is one set. The other set is 1, 5, 10, 20. Which set has higher variance? The second one has higher variance. So let's say I'll slightly change it. 1, 1, 2, 1. The other one is 1, 5, 10, 20. Which one has higher variance? Still the second one, right? So the closer they are, the variance is low. The spread there, the more spread there, the variance is high. Now which one has closer lengths here? Is it the blue? Right? So the closer means variance is low, right? So they all look similar, right? So after projecting it along this direction, they all look similar, which means that you are essentially losing the distinguishing capability between these 2 points in this direction, right? So you have lost that essential difference between these 2 points because they are all crowding up in the same, nearby to each other. On the other hand, if you find a direction where they crowd up along the line, but then they are spread out, then each point has its own unique distinguishability, right? So the more the variance, the better it is for you. That's a better line, right? So what you are essentially saying is that you can either reduce the error, or you can find the direction where once you project, the points don't lose their distinguishability characteristic in the sense of variance, right? So most of the information of the points is still there, right? So you can still distinguish between 2 points because they don't crowd up close to each other intuitively, right? So the higher the variance, the better is that line. Is that clear? Okay. So the simple way to also understand is that is just Pythagoras theorem, right? So take this point, the length square of this point is what we are saying, this bit plus this bit. This bit contributes to the variance, this bit contributes to the error. If you minimize the error, the length is the same. If you minimize the error, you have to maximize the variance. If you maximize the variance, the error will get minimized, right? So both are exactly the same things, right? So we can do either of these. So this is one other way to understand. So basically what we are essentially saying then is that you want to find directions where the variance is as high as possible. The first direction that you will find is the direction with the highest variance. The second direction you will find is the direction which is perpendicular to the first direction, which has the second highest variance. Why perpendicular? Because you're only looking at the residue, so it will become perpendicular, and so on, right? So you can keep doing this. One other way of looking at this is that what does this help us, right? So why does this help us? By looking at this variance view, now you can think of it this way, right? So now let's say you have height and weight. Now I choose to think of these height and weight as numbers as I don't know what these numbers are. So some okay, so some okay. So think of these green points for now, and now the x-axis is height, the y-axis is weight. Of course, they are centered, so you might have some negative values and so on. Nevertheless, you have a bunch of points. Now, the question is, if I tell you the height for a point, can you make any guess about the weight of that point in this data set? You can make some guess about at least the average, because if the height is increasing, the weight is increasing. Now, if I actually run this algorithm to find the best line, I will get this line as this vector that I am pointing here as the first line. Now, if I take the residues and then again run the algorithm, I will get this line. So, these two will be my lines, right. So, now if I choose to represent the same data as projections along these two lines, I will get this data. Now, my features have changed. Now, my features are not height and weight anymore. They are projections, they are combinations along some directions. You are weighing the features differently. In this case, you are weighing, in the first case, you are weighing it as using 1 by square root 2, 1 by square root 2, which is height plus weight over square root 2. And the second case, you are weighing it as 1 by square root 2 minus 1 by square root 2, which means that for each data point, I am storing height minus weight by square root of 2. In other words, initially I was collecting information from you. Every person I collected two numbers, height and weight. Now I am saying I am not going to store height and weight. I am going to store height plus weight as one number and height minus weight as one number. But why would I want to do that, right? So that's a question you should ask. Well, in the previous case, if I told you height, you can guess something about the weight, which means height gives information about weight. On the other hand, if I choose to store information as height plus weight and height minus weight, if I told you the value of height plus weight, you will not be able to guess anything about height minus weight. On an average, height minus weight is, that difference is only some error, right? So it can be either positive or negative. On the other hand, in this case, if I told you height, you can somehow guess what your weight might be. Here, the same points, but then I am storing it in a different, the axes have different names, right? So initially the axis was height and weight. Now the axes are height plus weight and height minus weight. Now in this way, I mean, if I store the data points like this, then knowing one direction will not give me any information about the other direction. In this particular case, the second direction is actually unnecessary, so I would only store one direction. But then what this is also telling us is that these directions that we are finding are actually decorrelating the data. You are finding the direction with the maximum variance, and now you are removing that direction, and then you are looking for the next direction in the perpendicular subspace of the original direction, which means that all the correlations between the first direction and the second directions are gone, right? So you are finding directions such that your data completely is decorrelated, the information is decorrelated in these directions, right? So in some sense you are extracting the maximum decorrelated information. So why would you want to store information which is, I mean, if you have height, if it's already giving you some information about weight, you might not as well store that, right? So the point is, you have to store something new only if it gives you some information which is completely not correlated to the previous one. So you want to find directions which are completely decorrelated, and the way to find that would be to find directions which first maximize variance, and then you look at the perpendicular space and then maximize variance in that direction and so on, right? So this will give you a decorrelated. Does that make sense? Any questions? At least at a high level. Okay, good. So where are we with respect to time? Okay, so now let's try to apply this to a real world data set. All the mathematics, I mean, people who slept through the mathematics can now wake up. So, so now we are just going to show some pictures. Okay, for the Disney lovers. Okay, so here is a real world example. So what are we going to do here? So this is a data set from the Yale University. So basically this is a bunch of faces. These are all faces of, I think, lab members of a particular lab of different races and so on, but then they are all black and in grayscale. So how do you, so each of these is a data point, right? So each face is a data point. It's some m cross n grid, right? So now that's a matrix, but then you can think of it as a m into n dimensional vector, right? So if it's like a 3 cross 4 matrix, you can think of it as a 12 dimensional vector, right? So there are only 12 numbers. You can think of it as a point in some 12 dimensional space. So if you think of it that way, so each point is something like a 32 dimensional space, right? So because the number of pixels in this is something like, I think it's 256 times something. So each point, each face is a point in some 32 dimensional space, right? So the values, of course, of these points are somewhere between 0 and 255 or 1, depending on how you want to represent grayscale. So they are all in 32 dimensional space. The number of data points that you have are 20,000. Around 20,000 faces were collected, right? So in this was a massive experiment. They did this. Now you have a bunch of data points, n data points in d dimension. You can run your PCA. What will your PCA give? Your PCA will give you W1, W2, ... Where is W1, right? So W1 is also in d dimensional space. In this case, our d is 32,000. So W1 is in a 32 dimensional space, which means I can get that 32 dimensional vector and then convert it again into a matrix format and try to visualize it. If I do that, I get this. This is the direction, first principal direction. This is the second, and so on. What can you observe from this? What are these pictures, these ghost looking pictures actually telling us? Sorry, who's saying? It's increasing the details. So what does that mean? So what is the first one capturing? Perhaps the first one is capturing the fact that somehow this data set has faces, right? So the most interesting thing about this data set is that it looks at faces, right? So now as you go along, the details get more and more precise, right? So maybe here this is probably something about the nose, maybe here it is more about, I don't know, the something below the nose and whatever it is, right? So the details get added as you get more and more principal components. Now what you can do is you don't need, the question is, do you need all 32,000 dimensions? Because it looks like even with one dimension, you somehow can figure out if it's a face or not, right? So what you can do is, here is a test image, right? So what I am doing is, this test image is the original image. Now I am trying to store this test image from 32 dimensional space. I am reducing it to a 25 dimensional space, which means I am projecting it onto the top 25 dimensional subspace, right? And then this is what it is, right? So perhaps if you want to do, let's say, a face recognition system using this, maybe this is 25 is not a good enough representation, maybe because if this guy, I mean, if you are pretending this guy is this picture, maybe the system might not do that well. But then as you go along, you observe that you don't really need to go too far, right? So with 1600 features, which is like a 50 time reduction from 32,000, you kind of get all the interesting details about this person. You don't need the exact image now. I can throw away that image. I don't need that 32,000 dimensional image. I'll just store this 1600 dimensional image. Now this is good enough. Now let's say, why is this good enough? Let's say instead of, let's say, a face, a human face, right? So let's say if I want to see, so okay, before that, so how did this picture come about? Can somebody explain? What do I mean when I say R is 1600? How did I get this picture? Correct. So basically you had 1600 vectors in 32 dimension, and then you projected it on each of these 1600 vectors. You get one number for each projection. So that all the set of 1600 numbers will now represent this image, and now you multiply it with the corresponding principal components. Now you weight these guys using the corresponding weights of this picture. 1006, I mean, I have only shown 4, but then imagine there are 1600 of these. For this particular data point, you project it onto this, you get some number, you scale it by that, project it onto the second one, you get a number, scale it on that, and then add all of these up. That's what is this guy, this face, right? So now you can see already that you don't necessarily need too many dimensions to represent human faces. Why did this happen? This happened because human faces has patterns. Though your face is different from mine, right? So we share a lot of common characteristics. Our face has general structure. There are eyes, nose, mouth, and so on. And so there is some low dimensional space where the essential information is, right? So everything else is detailed. If I want to really reconstruct you exactly, then I need all 32,000 dimensions. But then for all practical purposes, if I want to identify you, I don't want to reconstruct this photo. I don't care about this photo. I just want to identify you as a person. I don't need all 32,000 dimensions. That's what this is saying. I can only do with 1600 dimensions. Now, for example, let's say instead of a human face, let's say I started with a dog's face, right? So now this is an image. Now, what can you infer from this image? From this set, I'm doing the same thing. Now, I am projecting it onto the principal components and then trying to reconstruct. This is the original image. Now, what happens as I go along? What can you infer from this picture? So, for example, what is this? Look at this. So, if I only use 25 components, then I am pretending this dog is looking like this. What does that mean? Why is it looking like this? Because, so imagine I just showed you this picture. Would you have guessed this is a dog? This looks like a human face, but why is that? No, I'm not asking why it looks like a human face. I'm asking why is this algorithm returning a human looking face? Precisely, right? So the first 25, your data set just had human faces, right? So the most interesting information in your data set is captured by the principal components, which are the human-like features, right? So which means if you only use 25 dimensions to reconstruct this, what is it going to give? It's going to give the best human who looks like this dog. That's what this picture is, right? So if you want to, you can do the following also, right? So I don't know if maybe there should be apps doing this already, right? So you should. This looks like a business idea to me. Maybe the other way around, right? So you train a lot of dog faces, do PCA, and then project your face on the dogs, and then I'll tell you which is the dog that you best look like, right? So that's a fun experiment to do. Anyway, so but that's the idea, right? So you will get directions depending on your data. Your data is finally dictates the directions, and in this case, because we started with the human data set, you are getting this. But then as you go further, right? So after 1600, now though you have trained it on a human data sets, there are so many common features between human and dogs that with 1600 you are pretty much okay, right? So it's not as good as the comparison between this and this, but then you are still able to pretty much figure out what this dog is, right? Yeah, it's at least it's a dog, right? So maybe if you really want to run a classifier after this, which figures out from a photo if it's a dog or a human, then this is kind of telling you that 1600 features are good enough. You don't have to go beyond that, right? That's a huge dimensionality reduction. Any questions in this picture? Yeah. That's correct. Yeah. So because for the algorithm, it doesn't know it's a dog or a human. It's a point in 32 dimensional space, and I can try to represent it using these interesting directions. For the human faces, these are the interesting directions. For the dog faces, different directions would be interesting, right? Okay. Anything else? Good. We are almost done. So I just wanted to summarize whatever we did today. What we did is, we started with a simple question that you were given a data set and you do whatever, go figure out what you want to do, and then we said that we want to find like a compressed representation, and our notion of compressed representation is to find a subset that best represents this data, and for that we argued that you can either find a subspace that minimizes the error or directions that minimizes the error or maximizes the variance. Both are exactly equivalent. And in the way that I described it, I said that you choose the first direction and then you choose the second direction and then you keep going greedily. But typically in practice, you won't do that, right? So you use something called as a singular value decomposition. For people who have seen that, whatever we did exactly is finding the singular directions of the data set itself. But if you're not seeing that, that's okay, right? So in all I'm saying is that in the way I described the algorithm is not the way you would implement it. There are faster ways to do this, but then the essential directions that you get would be exactly the same. And at least from a pedagogical point of view, this is a better way to understand what's happening. Of course, as we saw one example, this is a very useful thing in practice. So we won't be able to talk a lot about the issues of this algorithm today, but at least I'll point out some issues and then I'll finish. One of the issues is, as I said, in practice you would do this using what is called as a singular value decomposition algorithm. Now there is a computational burden that might happen, especially when you have image like data sets where the number of features that you have is much larger than the number of data points that you have. Maybe you are in a company and then you want to develop a system that figures out if face recognition system for employees in a company. Maybe it's a medium sized company with 1,000 employees, but then each photo of the employee is, you're representing it by 32,000 dimensional image, right? So there are lesser data points, but then in high dimensions. So this PCA or the SVD is actually computationally expensive. That is one problem that typically might arise in practice. The second issue, the first issue is when D is much greater than N. The second issue is when here the whole assumption was, because we were not given any supervision, the whole assumption that we relied on is that there is some linear subspace, there is a bunch of lines which will give you a plane or a subspace in general which has all the information, essential information. This may or may not be true about your data, right? So maybe there is a non-linear structure, right? So maybe it's in a plane, but then it's not all around the plane, but maybe there is a nice structure in the plane itself, right? So in which case can you do better, right? So is there a different way? PCA will still give you some answers, right? So it's not going to say I won't do this problem, right? So it will give you some answers, but then maybe you can reduce your dimension further by taking advantage of the fact that the structure is perhaps not linear, but then non-linear, right? So these two look like, at least in first look, these two look like totally different issues. One is dealing with a computational problem where the number of features is much larger than the data points. The second one is about a structural problem. You are essentially assuming that it's not linear structure, but then some non-linear relation between the features. Maybe your data is height, weight, and I don't know, body mass index, where body mass index is actually something like, I don't know, height by weight squared or something like that, right? So it's no longer a linear relationship between these components. These two look like different problems a priori, but the interesting thing is that you can solve both of these using the same techniques. We won't be able to talk about, unfortunately, given the lack of time. The technique is called using what are called as kernels, not the linear algebraic version of kernels, so not the null space kernels. This is something called, this is a machine learning definition of kernels, which are not just useful for this problem, but are also tremendously useful in a lot of classification, supervised learning problems also, and you will encounter these as you look at the machine learning, further machine learning courses in your course. Essentially, the idea is, when you start, you are given a bunch of data points, you artificially project these data points to a very high dimensional space and then do PCA there. Now, the idea is that the non-linear structure in the low dimensional space can actually be captured using a linear structure in a high dimensional space. So you artificially project your data point to a high dimension and then do a standard PCA there, which means that because we are going to a high dimension, you need to solve the first issue. So somehow if you solve the first issue, the second issue will come for free, right? So the solution to the second issue is for free. And the trick that does this is what is called as, kernels, but I'll let you go and explore what kernels are when you have some time. Okay, so with this, we end this workshop. If there are any questions, comments, thoughts, we can take a couple of minutes. Anything? I hope it was useful. Any? Okay. Yeah. Okay, great. Thank you for patiently listening, and hopefully this will spike your interest in understanding more about PCA. I don't expect you to understand all details in a workshop like this, The idea is to introduce the big picture, and then you go back and dig the details for yourselves. Okay, thank you. All the best. See you soon. Bye.